is something that
So they should, yeah. So in this paper, I'll kind of return to this later. In this paper, the mass model was not an NFW profile, but I'll get back to this later.
So when this came in dark?
Yeah, so there's some upper limit on its luminosity. I'll get back to some of the details later. So I'll just say briefly that this technique depends a lot on the spatial resolution of your data. And so you can see this. Okay, so on the left is the source. This is a mock source. Okay, the top is something comparable to what the Hubble Space Telescope will give you. The bottom is if you have the same lens but at 4 times the resolution. And then this is a map of the minimum detectable halo mass. Okay, so you can see with HST-like data, it's sort of hard to tell the scale here, but the minimum mass is a few times 10 to the 9 solar masses, and this improves to a few times 10 to the 8 solar masses if you have much higher spatial resolution. So for gravitational imaging, the spatial resolution of your data is really the name of the game, and it's the limiting factor in how low you can go in halo mass. So, okay, this is a couple kind of summaries, right? I'm going to return to gravitational imaging later. So I'm going to keep going for now. Right. So now I want to talk about the kind of the second way that you can analyze quads, which is by looking at the relative brightness among the lensed images. Right. And as I said before, because these depend on the second derivatives of the potential, they're sensitive basically to the local mass, whether it's dark matter or luminous matter, and we can use this to go below 10 to the 8 solar masses. In particular, as I said before, we're thinking like down to 10 to the 7 with current data. And to illustrate this, I made another movie. Okay, so what's going to happen in this movie is I'm going to drag a 10 to the 8 solar mass halo across the simulated length image. All right, so you'll notice this looks like an arc. The angular scale here is like a few hundred million arc seconds. So this is not the same kind of arc that I was showing before. This is essentially what one of the multiple images would look like if you had no point spread function and you could just see the lens light directly. Okay. So as the halo goes across, if you watch on the left panel, you'll see the change in brightness of the image as a function of the halo's position from this lensed image. Okay. And if you stare on the right, you can see it barely get brighter and dimmer, but so this curve on the left, you can think it's something like the magnification cross-section for a 10 to the 8 solar mass halo. Right? And you can see that it's about a 10% change in the brightness. Right? So for reference, we can measure the brightness of these images to around 4 or 5%. And so this kind of signal would be detectable in the data. And the other thing I want to highlight is that if I were to make that same movie with the same total halo mass, but change its internal structure, you would get a different magnification cross-section. All right, so the black curve is what I just showed you, and then the green and the magenta is if I change the concentration of the halo. So this just tells you how the mass is distributed inside the object. Right? And what you should take away from this is that more concentrated halos are more efficient lenses. And then the converse is true as well. So if you have a halo that's less concentrated, it's a less efficient lens. So I'm going to take a few slides now to explain how we go from an image of a lens with this intuition that the halos are perturbing the relative brightness among the images to constraints. Okay. And basically what we're going to do is try and forward model the data by doing ray tracing simulations where we simulate this lens with dark matter structure all the way along the line of sight, as well as the subhalos that are associated with the main galaxy. Right? So the subhalos in this schematic are in this pancake, and then the line of sight halos is everything else along the line of sight. And basically, you'll start with some dark matter theory, right, that makes some predictions for how many halos there are and what their internal structure should be. All right, so that gets you to the second point. Then we build those predictions into the model that we use to generate all the structure. And then we'll simulate a certain lens hundreds of thousands to millions of times with different dark matter structure included in the lens model. Right? And so we'll have a huge amount of simulated data that we can then compare with the real data and then draw conclusions about how likely that dark matter model is based on how frequently it can explain the observed data. Okay. So it's a statistical way of looking for substructure rather than a kind of high significance detection of single objects.
But at this point, you don't include the source properties at all.
So here the source is basically a very, very compact quasar. And so it's a relatively simple source to model. It's just roughly a Gaussian. We model as a circular Gaussian blob of light with some size. So these simulations, a lot goes into them. I sort of grouped them by stuff that we're interested in on the left and things that are for us nuisance parameters on the right. Okay, so on the left, we have things like the halo mass function, which is how many dark matter halos there are per unit halo mass. There's the concentration mass relation, which tells you how dense halos are as a function of their mass. There's any additional physics that might enter the problem based on which dark matter model you're looking at. And then things that you have to marginalize over are things like baryonic physics that might alter the number of subhalos through tidal stripping, for example. You have the size of the lens source. So we know based on the wavelengths that we're looking at the images roughly what the size of the source is, but we don't know exactly the size. So we have to account for this uncertainty. Then there's measurements uncertainties, and then there's, of course, the structure of the galaxy. This returns back to the point that you made, which is, can you conflate substructure with a different model for the lens? So we have to then marginalize over different properties of the main deflector when we do this. And the largest source of uncertainty comes from how you account for that source of it, how you account for the structure of the deflector. So what you get out of these simulations is stuff like this. So these are two probability distributions for the relative brightness among two images, okay? So it doesn't really matter yet what the models are, but you can see that model 1 and model 2 are making different predictions for how bright this image should be, okay? Now, suppose that you measured the true flux ratio and it landed here, okay? You would conclude based on this that model 1, okay, is about 10 times more likely than model 2 to explain this data point. So what we're really doing here is we're forward modeling these histograms, which is basically a proxy for the likelihood function, right? And then once we have, you know, these predictions, we try and match all three flux ratios, and we accept realizations of structure and then the parameters that correspond to them based on how frequently they fit, they can explain the observed data. So this technique is called approximate Bayesian computing. It's essentially a way to handle intractable likelihood functions if you have a very high dimensional space that you're trying to explore. So once you do that for a single lens, you can apply the same machinery to multiple lenses, and then you just multiply their likelihood functions. And once you have the likelihood, you can then choose a prior, and you can do Bayesian inference, you can compute confidence intervals and stuff like this. So that's in a nutshell how the machinery works. You can apply it to like many different dark matter models. They all make different predictions for the properties of halos. I'm going to focus for the rest of the talk on self-interacting dark matter, okay? And I picked self-interacting dark matter because I think it's phenomenologically a very interesting theory or class of theories. And I think it's also gained a lot of traction in recent years, which I will discuss. So what do I mean by self-interacting dark matter? So when I talk about self-interacting dark matter, what I have in mind is something that only interacts with the standard model through gravity, or if you like, it has such a weak interaction with the standard model that you'll essentially never detect it, okay? So this is like the worst case, the nightmare scenario, I think, for the LHC or direct detection, right? Like you might never see this in a collider or in a direct detection experiment. It must give a large scale structure of the universe that is similar to cold dark matter, okay? And on large scales, it should be approximately collisionless or effectively collisionless, right? And I'm showing the bullet cluster here because some of the strongest constraints on self-interacting dark matter come from the bullet cluster. I mean, basically, the fact that these two concentrations of dark matter seem to have passed through each other allows you to put upper limits on the degree to which dark matter particles can scatter against each other. Okay, but the other thing that needs to be true for self-interacting dark matter to, you know, perhaps explain the properties of low mass galaxies is that you need a very large cross section at lower speeds. Okay. So here, the connection between halo mass and speed is coming from the central velocity dispersion of the halo. So galaxy clusters are very huge. They have high central velocity dispersions, so they probe the self-interaction cross-section at high speeds. Dwarf galaxies and dark halos are very low mass. They have low velocity dispersions, and they are probing the self-interaction cross-section at low speeds. Right, so the way that you achieve this is by having a velocity-dependent self-interaction cross-section, right, which is strongly suppressed at high speeds. So you evade constraints from the bullet cluster, but then it can get very, very large on the scales of galaxies, dwarf galaxies, and then the completely dark halos that we're looking for.
These velocity dependent cross-section, we see in a lot of systems, collision systems.
Would you see it in collision?
I mean, I have difficulty, is this a part of parameterization or this is a property of the dark matter particles themselves?
So this, you mean the cross-section?
The cross-section that depends on velocity, or is it something standard?
So velocity-dependent cross-section can arise in a variety of ways. So this particular one is if you have some like long-range force, okay, with some light mediator. Right, so if you write down a Yukawa potential for this interaction, for example, it can give you, I mean, actually this cross-section is something that emerges from an interaction like this, right, with some light mediator and a long-range force. So that's the kind of the class of models I'm going to focus on. Is that what you're asking?
No, I was just thinking in the back of my mind that it could be wrong with its topic, right? When we have dynamical friction, for example, with a second one, if you go slowly, the interaction is the friction is stronger. If you go faster, the friction is less. So I mean, in collision systems.
You mean like gravitational scattering?
Gravitational scattering. And I was wondering whether this was the same effect.
No. So, well, right. So it's not gravitational scattering now. There's actually some mechanism for dark matter particles to interact. Yeah. All right. So this thing on the right is actually a movie, and I made this movie to illustrate kind of the interesting phenomenology that can emerge from this particular class of dark matter models. Right. So what happens is I play the movie is I'm going to ramp up the strength of the potential. And then just scale the mass of the dark matter particles so that the amplitude is fixed at high speeds. Right? And because this is an attractive potential, you'll actually form bound states in the scattering problem. And these bound states produce resonant features in the cross-section at different speeds. All right, so as you see, as you move through different regions of parameter space, you explore different resonances at different velocities. And these can then differentiate the scattering cross-section amplitude at different velocities and therefore different halo masses by many orders of magnitude. Right. So this kind of model makes very testable predictions for both galaxies, dwarf galaxies, and very low mass dark matter halos. Right. In principle, you should see different effects in different mass halos if you have this resonant structure in the cross section, because the amplitude is changing very quickly with velocity and therefore with halo mass.
And this velocity is the velocity dispersion, not the velocity of the halo with respect to.
Strictly speaking, it's the relative velocity between dark matter particles, which is related to the velocity dispersion with some prefactor.
Okay.
Yeah. And I'll just say that, I mean, this class of theories has been around. I mean, people have recognized for about 10 years that they're interesting, but not a lot of work has been done on actually exploring the consequences for structure formation. So this was the original paper around 10 years ago that showed the movie in a slightly different way. So here you see the resonances appearing essentially in a different projection of the space. So for what follows, I'm going to take 5 models, which are essentially 5 different frames from the movie I just showed you. And these are going to be representative of many of the different types of cross sections that emerge from this attractive long-range dark force. And they are, as I'll discuss, they're representative in the sense that at low speeds, they have a kind of variety of different behavior, right? So you either have something that just increases forever at low speeds. You have these resonances with single spikes. You have multiple multimodal resonances, and then some of them have these anti-resonances at low speeds. Okay, so this is sort of a representative selection of models. And if we want to study these with lensing, we have to understand how self-interacting dark matter changes halo density profiles. Right? So if you were to take a cold dark matter halo, it would look like this basically forever. And so on the y-axis is density, and the x-axis is the distance from the center of the halo. So it has this profile and it will live like this basically until the end of time. Right? But if you turn on self-interactions, now you have a way to distribute energy throughout the halo profile. And so first, heat will flow towards the center. As this happens, you start to flatten the central cusp of the cold dark matter halo. So you start forming a core. This is, to date, basically the telltale smoking gun of self-interacting dark matter is if you find cores and halos. This process will go on for a pretty long time. Eventually, the core will reach kind of its maximum size. You see the velocity dispersion in this case is basically flat towards the center. And once this happens, once you reach this stage, something very interesting happens, and you actually have a runaway contraction of the halo's density profile. And so this process is called core collapse. When it was first proposed, I guess 40 years ago almost, this was called the gravithermal catastrophe, and that's because it's an out of equilibrium runaway contraction of the halo. And then it was about 30 years later that it was pointed out that self-interacting dark matter is actually a more natural way to produce this effect than the original mechanism that Lyndon Bell had in mind in 1968. So this idea has been around for a while. And to make a connection with lensing, I'm going to take this schematic that I was showing you earlier, and then I'm going to project all the mass along the line of sight, and then we're going to look down the line of sight. I did my best to animate this, so bear with me. So we're going to project it, okay, and then we're going to look down the line of sight. So now we're looking down basically towards the source. I've colored all of the dark matter structure here in red. So things that are red generally are halos. And then the color scale is like the dark matter density relative to the average density of the universe. So halos are overdense, things outside of halos are a little bit underdense, okay? And this is in cold dark matter. So if I take all of these halos and I randomly make some of them core collapse, you change this picture. Okay, sorry, before I go to that, this curve here, this is called a critical curve. So if this were a lens, you would see images near the critical curve. Okay, so keep that in mind. If I make that same picture, but now I allow some halos to core collapse, you get this realization on the right. Okay, so you can see just by eye that the halos, some halos have become much, much denser than in cold dark matter. And you can also see, if you look at these places I highlighted, that if the halos are near the critical curve, they will produce this deformation in the critical curve. And essentially, this deformation of the critical curve, you can associate with a very strong perturbation to the brightness of an image, if it happened to be nearby that position, okay? So more quantitatively, if I make this magnification cross-section movie again, okay, and I did it with a core collapsed halo, or sort of a reasonable implementation of what a core collapsed halo might look like, you would get this red magnification cross-section instead of the green. Yes.
So the core collapse is due to the gravithermal catastrophe.
Yes.
But we know that from globular cluster, the gravithermal catastrophe doesn't really happen because of free body interactions and ejection of the stars. Right? So wouldn't you expect that something similar would happen in that matter as well?
So I hadn't actually heard about that specific mechanism of preventing core collapse. I will say that if you set up an n-body simulation with self-interactions, the things do collapse. So it seems fairly
Maybe I'm
easy.
wrong. I seem to remember being a increment, for example, standard textbook where they talk about they have negative heat capacity, core collapse, gravithermal catastrophe in theory will appear, but it's but we don't really see the globular clusters, and I was under the impression that this wasn't good, but I'm not a theorist.
Depends. Because I know about that because of the way to form the post in the sense of global clusters. So it depends on the profile of the global cluster. So for certain profiles, the report interactions prevent that, but for some other profiles, actually the gravithermal collapse wins. So you can count on collapse.
So yeah, I actually wasn't aware of this, but so far in simulations with self-interactions, you can make these things collapse. Yeah.
It also depends on the panel actually.
So, as I alluded to before, more concentrated halos are more efficient lenses, right? So a collapsed halo is, in some sense, the most efficient lens you can have that isn't a black hole, right? And so now I want to connect this back to the gravitational imaging that I talked about a little bit earlier. So this is the detection of the substructure that I mentioned on the left. It's the same one. Okay, so this system was actually reanalyzed, I guess now 2 years ago by Quinn Miner. And they asked like, okay, so there's this halo there. What mass and what concentration does it need to have, assuming an NFW profile to fit the data? And what you find here, so this is on the x-axis is the halo mass, the y-axis is the concentration of the halo. This band here is what CDM predicts. This is the plus or minus, I think it's 2 sigma or 1 sigma. I forgot exactly what the confidence here is. But basically, in order to fit this data, you need something that is many sigmas more concentrated than what you expect in cold dark matter. And you might be wondering, well, can you do this with baryons? Like if you put stars into the halo, can you explain how dense it is? The answer is not really, because then you need something that is an outlier, a huge outlier in the stellar mass to light ratio. So either it's an anomalously dense dark matter halo or it's an anomalously dark galaxy. Okay, so either way, it's very weird, right? And this paper said, well, one possible way to have very dense halos like this is if there's self-interacting dark matter and they core collapse. Okay, so if we take this at face value, I'm not saying that I think this is like evidence for self-interacting dark matter, but if that is true, right? You might wonder, okay, well, maybe there are more self-interacting, maybe there are more core collapse halos out there, and in fact, there should be, right? I mean, if you find one halo that's relatively massive that is core collapsed, because velocity-dependent cross sections increase at lower speeds, you should find even more lower mass halos that are core collapsed. So this is the kind of question that I wanted to address. So I'm going to talk a little bit about how we try and do this with quadruple image quasars and whatever time I have left. If we want to study self-interacting dark matter with quads, right, we need a way to go from these cross sections that I introduced earlier to the process of core collapse. So we need to basically model or predict core collapse for these cross sections. Then it's just a matter of plugging this structure formation model into the simulations. We then simulate the lenses that we observe millions of times, right? And then we determine how likely it is that self-interacting dark matter can explain the data. Okay. So a bit first about how we model core collapse. So it turns out that if you choose, or if you track the evolution of a self-interacting dark matter halo, the time evolution looks self-similar if you scale time by units that depend on the cross-section. So essentially, there's this evolution time scale, which depends on 1 over the density and a velocity scale for the halo. And then this other term is a thermal average of the cross-section. It's weighted by a factor of relative velocity to the 5th power, just for some sort of technical reasons. But the point is that if you track time in these units, then core collapse always occurs at the same time, right? And it will be some multiple of this evolution time scale. And when we try to keep track of this core collapse time scale, there's 2 populations of objects in mind. And as I'll discuss, we need a different time scale for both. Okay, so first we have subhalos. So these are things that are gravitationally bound to the host halo. But the host halo is the halo that's around the galaxy producing the lens. So subhalos are bound to this host halo. They get tidally disrupted by the host, right? And then their particles bound to the subhalo can also scatter against particles in the host. Right? So there's a lot of complicated effects that afflict subhalos that don't really matter for field halos, because field halos are just kind of floating out in intergalactic space, and they're not subject to these kind of complications. So with this in mind, there's going to be essentially 2 parameters that are important for this model. One of them is the time scale for core collapse in field halos. So this is called lambda field. And basically simulations predict it should be order 100, so 300 or so. Okay, and this is basically just set by how long it takes core collapse to occur in a dark matter halo. And then a second time scale that is going to be defined relative to core collapse in field halos is the core collapse time for subhalos. And so that is controlled by another number, which tells you how quickly a subhalo collapses relative to a field halo. And this number is much more difficult to predict because it depends on the things I mentioned earlier. So the tidal stripping of subhalos by the host, it depends on interactions between the subhalo particles and the host. This can in principle depend on the cross section. So whereas lambda field maybe doesn't depend on, for example, the velocity depends on the cross section, these effects that are relevant for subhalos could depend on the cross section. So the point is that lambda sub is very uncertain from a theoretical standpoint. And so it's going to be a free parameter, and we're just going to see what effect it has on the data if it takes on different values. Okay. There's also some other stuff in the model I'm not going to go into. But basically, if you write down this sort of simple mapping from cross sections to core collapse, you can turn each cross section into the fraction of collapsed objects as a function of halo mass. Okay, so just focusing on a few examples. So model 1, it goes like 1 over v at low speeds, and then it transitions to 1 over v to the 4th at high speeds. It reaches extremely high amplitudes at low speeds. And in this case, you see basically everything less massive than 10^8 solar masses is collapsing. Right? If you have a resonance, so for example, if you look at model 2, this has a resonance enhancement by about a factor of 20 or 30 at around 20 kilometers per second. And so then this kind of structure formation model predicts that essentially everything in a certain mass range will core collapse, but then nothing outside of that mass range will core collapse. Right, so this sort of, so I mean, I'm testing this with lensing, but I just want to briefly mention that, I mean, this is also a prediction that you could test with dwarf galaxies at different masses, right? If you have a bimodal distribution of collapsed objects at different masses, you could, that I think would be strong evidence for this kind of cross-section with resonances at different speeds. Okay. All right, so another just visualization, right? I can take that same population of cold dark matter halos and then randomly make objects core collapse based on these probability distributions for how many objects are core collapsing in different mass spins. And you can just see, okay, so model 1, lots of low mass things collapse, right? I'll remind you, model 1 is black, so everything less massive than 10^8 is collapsing. If you look at, okay, model 5, this is this curve here, the turquoise one. There's no low mass things collapsing, and then the only things collapsing are relatively massive halos. All right, so if you look here at model 5, you can just see, okay, the only things collapsing are these relatively massive objects. Okay, so seems to make sense. And what you get out of this analysis is this constraints on the relative likelihood of the time scales. All right, so I'm going to explain how to read these plots now. So on the far upper right-hand corner, okay. Okay, so first of all, every pixel is the relative likelihood of that combination of core collapse timescales relative to the most likely combination. Okay. So this is a map of the relative likelihood. Cold dark matter lives in the upper right. The reason why you can associate that with cold dark matter is because here the core collapse timescales are very long. So nothing is collapsing, and this is sort of by definition what you mean by cold dark matter, where you don't have any core collapse halos. Okay. The opposite is true in the lower left corner. So this is where the timescales are both very short, which means basically everything collapses immediately, and so every single dark matter halo in the universe would be core collapsed, right, on the lower left corner. So the y-axis here is lambda field. So this is the core collapse timescale for field halos. It sort of sets the overall normalization of the collapse times. So the y-axis is basically how fast all halos are collapsing. And then as you go along the x-axis, this is the collapse timescale for subhalos. And again, it's how fast a subhalo collapses relative to the field halo of the same mass. And to assign some sort of physical meaning to these axes, okay, as you go up and down the y-axis, this is essentially changing the nature of dark matter. So as I said before, if you have elastic self-interactions that don't radiate energy, okay, their collapse timescale should be order 100, 300 or so, right? So that would live on the upper part of the y-axis, whereas if you have inelastic self-interactions that dissipate energy on each collision, that turns out to accelerate the process of core collapse, so those models will live on the lower part of the y-axis. Okay. Now, for each choice you make about your self-interaction, you also need to understand how core collapse proceeds in subhalos. Right? So you can see, if you're all the way on the left, this is a situation where the tidal stripping of subhalos basically accelerates core collapse in those objects, so they all collapse. Okay. As you go to the right, this is a situation where scattering between subhalo particles in the host halo prolongs the life of the core, so it delays core collapse. Right, so that's what happens when you go to the right. And you can see here that, I mean, has a pretty clear effect on the data. So in particular, if you have models where everything is collapsing, this is disfavored with relative likelihoods that exceed, it exceeds 10 to 1 in the bottom left corner, and then it kind of becomes less penalized as you move towards the upper right. So essentially the data, and then this applies to every cross-section you looked at, they all are penalizing models where a large fraction of halos are core collapsing. Okay, so if I just flip through the different constraints, then you see that they are all somewhat different. The fact that they are different means that, at least in principle, you can differentiate between these types of cross sections with lensing, although with the current data, we can't say anything more really than the data disfavors scenarios where most of the dark matter halos in the universe have core collapsed. So it can't be, it's very unlikely to be one of these dissipative self-interaction models, and it's very unlikely to have an extremely high cross-section amplitude at low speeds if dark matter has self-interactions.
What do they compare to the top right corner we see the data?
The data. Well, so
I mean, where would the data sit in this flow?
what do you mean? So this is the likelihood of the data. This is like a
Okay, it's not simulation. Okay.
yeah. So this is with real data. Sorry, I should have said that. Right? So
Yeah.
this is with the 10 lenses that we have suitable data
Okay.
for.
I thought it was a simulation, but you can find.
No, yeah, sorry. No. So this is like our likelihood from the data. So, yeah. So I'll just say, I mean, yeah, CDM is okay. What's tricky about looking at it in this way is that just because it's more likely doesn't mean it's likely, right? It is like CDM seems to explain the data well, but what this is telling you is just that CDM is much more likely than these self-interacting dark matter models that we looked at. Yeah. Does that make sense? Right. So, I mean, just the conclusions for this is that existing data penalizes situations where many halos core collapse. And so, I mean, this can arise either through large resonances or kind of 1/v dependence in the cross section. All right. So I have like 2 minutes left. I just want to talk about the future. Okay. So the future is brought on by JWST. And the way JWST is going to help us is by measuring sources with different sizes. Okay. So I said before that the current data we have is sensitive to around 10⁷ solar mass halos. And the reason for that is with the Hubble Space Telescope, we can measure a region around the background quasar that's illuminated with a spatial extent of around 100 parsecs. It's the nuclear narrow line region around the background quasar, right? So if you imagine that this is a 10⁶ solar mass halo, right? Its deflection angle is much smaller than the angular size of the source. And that's why we can't detect them, right? What determines the detectability of a halo and the relative brightness of images is the deflection angle produced by that halo relative to the size of the source, right? You can imagine if you have a floodlight and you hold up a tiny magnifying glass in front of it, you can't tell that the magnifying glass is there. But now if you have a flashlight and hold up the same magnifying glass, then you can tell that there's lensing happening, right? So the reason JWST is powerful is because we can look at the mid-infrared emission, which comes from a much more compact region around the background quasar. So if I make this cartoon now with JWST, the source is now around 10 times more compact, and its angular size is now comparable to the deflection angle produced by a 10⁶ solar mass halo. So that is why we think that we'll be able to detect these lower mass objects with JWST. And so Anna Nirenberg is the PI of this program. And then by this summer, there should be about 10 to 20 more lenses with measurements from JWST. That's compared to the 10 lenses that we currently have. So yeah, the data itself is more constraining. It will also measure the relative brightness more precisely than Hubble. And so you get an increase both in the constraining power, the precision, and then just more a larger sample of lenses to do statistics with. So there's some forecasts I made for self-interacting dark matter. I'm not going to go into details, but basically you'll get much stronger constraints in the future than what we currently have. And then these are my takeaways. So I will just leave those here for now. Thanks.
So does anyone have some questions? Then we could-
Yes.
Thanks, Daniel, for this talk. I have two questions. The first one is a simple one. I don't know if you have an answer about. Can we figure out if the halo, the subhalo, if it's a subhalo or a field halo or a field halo, the one that disturbs
Mhm.
the images? Because we have the main deflector, the main lensing effect, we have the secondary effect, the perturbation of the flux ratio.
Yeah.
Can we figure out whether it happens inside the main halo, inside the main deflector, or outside?
So
along the
are you referring to
reflector?
lensed arcs with halos on them? Or are you referring to the flux ratios?
The flux ratios, itself.
So with the flux ratios, you're never detecting an individual object, right? You're detecting perturbations from the population. And that population includes things along the line of sight. So, yeah. So you could ask the question like, are there line of sight halos? Right? But you wouldn't be able to look at a particular image and say, you know, okay, its brightness differs from what we can explain with the smooth lens model. Like, was that caused by one halo along the line of sight, or like 10 subhalos, or was it 2 subhalos and 4 halos along the line of sight? Right? Like, it's difficult to disentangle that. Yeah.
Sorry, you have kind of a degeneracy between the position along the line of sight and the concentration, is it? No. If you assume one object, let's say, not a sum of them.
Yeah, I mean, probably. It's a little hard to say, right?
Because I'm thinking that in this new study, you show that revised this vegetal paper where they see that they found this very high concentration
Yeah.
for this perturber. How do they get this? They cannot distinguish if it's only one, where is the location, or they assume that in any case it's there.
No, so you can fit for the redshift of the halo. So in that paper that I was referring to, they explored whether it could be a line of sight object, and they concluded that it can be. It cannot be a line of, or assuming that it's an object along the line of sight does not alleviate the weirdness of that object. Right? It doesn't matter where you put it. I mean, in some cases, it's a worse for the data, and regardless of where it's situated along the line of sight, it appears to be an outlier in every sense of its properties. Yeah.
And I have a second one. What if someone else wants to ask? Okay. Can you go back to the gravitational limit?
Yeah.
Yeah.
Like, this stuff.
Somewhere that you had something that sub-yellow of mass 10 to the 10 solar masses.
This.
This one, yes. The distortion or the angular separation of the multiple images seems to be on the order of 100 milliseconds in this video. Or no?
Well, yeah, I mean,
The
it's a little-
size of the distortion, the effect of the secondary effect of the sub-yellow.
yeah. I mean, I don't actually see how to get that information out of these pictures, right? So this is a map of the projected mass. It's not the. So this is not light, right? This is mass. This
Okay, it's not light.
yeah.
Okay. Okay, but based on that, the 10 to the 10 solar mass is halo. How much can separate two images, two items? The angular separation that we expect for a strong density event.
I guess it depends on the concentration of the halo.
Yeah, so for CDM one.
So I think in CDM, even 10 to the 10 solar mass halos are not dense enough to produce multiple images. Think-
For
they would-
concentration mass
would
relations
have
that
to-
are.
Yeah, I think, I mean, I don't know off the top of my head, but I think most NFW halos are subcritical up until they become very, very, very massive.
Or
But-
very dense, so two concentration.
Right, so yeah, I mean, if you make them denser, then yes, they can produce multiple images, but yeah.
So here you could have, for example, up to 30, but then it would be brighter than this, right? That's the problem.
Yeah, so there's a long discussion of this in the kind of reanalysis of the system. Yeah, so if you assume that it's baryons, they compared it with simulations, with hydrodynamic simulations where the halos contain baryons, and they find that, yeah, so it's either an outlier in its concentration, or it's a huge outlier in mass to light ratio, and you assume that it's done with baryons. So either way, it's like a weird object. You know, and then there is a lot of talk whether this is just a selection effect. Like you're much more likely to find these halos if they're very concentrated. Right, so maybe this one is the one that you found is really concentrated just because it's much more likely to be found. But then you still have to explain how such an object exists. Right? So yeah, I mean, it's an interesting story. I wouldn't personally go either way on the, like whether it's a telltale signal self-interacting dark matter, but I mean, this is like an example of the kind of thing that people are thinking about currently with imaging.
I have another question.
Sure.
Yeah.
Yeah, that's one. Then if you think about your two-dimensional constraints, it's the lambda,
Yeah.
subhalo and lambda theory. You said that something about that model is because it's more like it doesn't do its life.
Right.
Therefore, ask this backward because you don't remember what your likelihood scale was. Does the fact that the core collapse halos are less likely, does it mean that they are very unlikely?
Yes. Yeah. Yeah. Sorry. I mean, maybe what I said just added unnecessary confusion. Like what I meant is that, so this is a map of relative likelihoods, right? So whatever the most likely point in the parameter space here, right, has a value of 1. Okay. So, and it turns out that that's always in where CDM works. And so if you think that that has a value of 1, then these models that live on the lower left corner are 10 times less likely.
So that's it, the factor of 10.
That's it. It's a factor of 10. Yeah.
Just because you don't have that one system, right?
Yeah. Sorry, what I said about like that was probably confusing. I mean, just saying that like the relative likelihood doesn't necessarily tell you how likely it is, right? It just tells you how much more likely one model is over another. Yeah.
Right. So the actual question now, so that was just the understanding what this is telling you. So I'm finding it a little bit difficult to understand what physics makes determining the x-axis difficult. So the subhalo, right? Because there the physics is, right? How the subhalos are affected by their being in a larger potential. Is that also a function of the properties of the dark matter, or is it a matter of simulating them in kind of resolution? So why is the x-axis difficult?
Yeah, so I guess, okay, I'll say it's, in principle, it's not difficult, right? You just need to like prepare a simulation that includes all of the relevant physics and then run it and see, right? But in practice, it's quite difficult to actually simulate this because there are a lot of different effects that you have to keep track of. Right? So for example, you have a subhalo, it's being accreted onto a host halo, right? As it falls in at whatever, 200 kilometers per second or something, those particles start being stripped from the subhalo from interactions with the host, okay? At the same time, the subhalo is heated by interactions with the host, and then it's also tidally stripped by a galaxy at the center of the host halo. And so keeping track of all of these effects in your simulation while resolving the central density of these subhalos is just difficult to do. I mean, in principle, you just run the simulation, right, and do it. And in that sense, it's easy, right? But I think in practice, it's difficult to do it accurately and in a way that's reproducible, right? Where someone else can run the same simulation and find the same trends and find that, you know, there's just a lot of moving parts and it's relatively new, I think. So people haven't really done it yet.
What would be that resolution that you need in order to work with this effect in simulation?
So I think this is now stepping a little bit outside my field of knowledge, but I mean, I think if you want to resolve the core because that's what you are really interested in, right? Is the collapse center. Then you need, so you need a very small softening length because you need to resolve the structure of the halo down to very small length scales. And then if you want to resolve very low mass halos, then you need a very low particle mass. Right. And so I think both of these things make the numerical evolution of all of them difficult.
So the reason why I'm insisting on it is that Carolina's moving lenses are not just because field halos are so much more abundant than subhalos, are basically going to be only sensitive to what happens to halos in the field.
Yeah.
So one would imagine ideal world, 10 years from now, we know exactly what we need on the y-axis. And then with your stuff, we know exactly what we need on the plane. So if for some reason the x-axis is difficult to determine, then we have experimental waves where we're sitting from that. Very long-term thinking.
Yeah, no.
I'm wondering whether there is some very interesting physics that we cannot access otherwise, that we can access with the synergy of the approaches.
Yeah, I mean, I think that's a great point. Yeah, I mean, I haven't thought about this in a whole lot of detail, but I mean, I will just say that the SMILE program is a very clean probe in the sense that it's just looking for these things out in the field, which are much easier to understand from first principles, right? And so, yeah, I mean, in that sense, I think it's a good project. But yeah, how that information is then combined with this, yeah, it's an interesting question. Yeah.
Let me take one question from here. Maybe you can try to mute, but I'm not sure. No, okay.
I'm just gonna
So
plug my laptop in. 'Cause
yeah. So I will take one question from Demosthenes. I hope it's still valid. The question, it was during the talk. So he's asking, so he say, I realize that the assumption is that the halos are spherical, but can we extrapolate the true shape of the halo with this method?
Right, so the substructures, we assume they're spherical. Yeah, so the things along the line of sight and also the subhalos. Yeah, I mean, so we've never tested what happens if you make the halos not spherical. My intuition says that this would not, that effect of turning a spherical subhalo into a slightly elliptical subhalo would be much smaller than sort of the other unknowns. Like if we're trying to measure how many subhalos exist, this will be the kind of first order thing that you measure, and then things like the ellipticity of the subhalos will enter at lower order. But to be honest, we haven't actually tested this before.
Yeah.
Please go back to a bit back to the different model, how the different models make this critical.
Oh yeah,
Yeah,
something like this.
so I don't know how relevant this is, but could this be reproduced, this kind of feature reproduced by, it goes back to Nick's first question. So by the line of sight, wake lensing, caused by cosmic series.
So not weak. So this is like a very different regime from weak lensing. I mean, so these panels include line of sight halos. I don't know if that was sort of what we were.
Yeah, but could this effect be solely due to the line of sight? Like can make you think you have the right model, but it's just
yeah, so you could imagine a scenario where there are no subhalos, right? And you would get similar pictures. You would just have less stuff in them. And that's ultimately something that you can measure. Because if you have lenses at different redshift, they'll receive different contributions from line of sight structure versus subhalos. So at least in principle, you can disentangle the two, how many there are. Right, you need many at different redshifts, right? Did I answer your question?
Yeah.
I want to.
Sure.
How to find these strong lens systems understand with the JWST, the program to find how to look for it.
So the JWST program is following up the known lenses. So they're already found. They just have not been hit with a good enough telescope to get the right data. So
The right angular resolution.
so it's a combination of angular resolution, and then you also have to look at the lens in a particular, so you have to measure the relative brightness in a particular wavelength. Because if you just look at the total flux of each image, some of that is being micro-lensed because it comes from, for example, the accretion disk around the quasar. And so, for example, you need Hubble because with Hubble, you can actually take the spectrum of each image and then measure the brightness in certain emission lines that are coming from the nuclear nanoline emission. And then with JWST, you do a similar thing in the mid-infrared. And so when I say like it doesn't have the right data, it means that it wasn't observed with Hubble.
But the discovery of these systems is completely scientific.
Yeah. So the discovery, you don't need Hubble. You basically look for, if I go back to, you look for point sources that are like, basically look for stuff that looks like that, right? Like these kind of bright quasar-like point sources that are kind of clustered together, either in a group of 4 or a group of 2 around some other bright thing. And then you have to check that the point sources have the same spectra or in the same redshift. And then there's other cuts you can make on the color and stuff like that. Like it could be 2 stars, right? That just happen to be. So there's a whole field in like how to find lenses in wide field circles. A lot of people are using machine learning. So they'll simulate a bunch of lenses, show this to the machine, and then show the machine the wide field survey, and then the machine says, these things are lenses, those things are just stars that happen to look like a lens.
I was assume that because these surveys are kind of seeing limited surveys, but you can't really get high resolution.
Right, yeah, you can't get high resolution, but it turns out you don't need that high resolution, right? Of course, you can't find the little lenses if you can't separate the images, but really, like once the images are separated by a few pixels, then you can.
So I guess you can find a lot of new.
Yeah, like hundreds, I think. Yeah.
I have one quick follow-up question.
Sure.
Completely kind of unrelated. Do we have any idea of substructures of our own model?
Of what? Sorry?
Our halo in which Milky Way is sitting.
Yeah.
Do we have any idea of how to find that, for example? I guess technique would be different.
Yeah. So, okay, so there are people that propose using lensing. Basically, if you have stars, kind of imagine the stars on the other side of the galaxy, and if they pass behind a Milky Way subhalo, they won't be multiply imaged, but then their apparent positions will be deflected in a correlated way as the subhalo goes across. So you'll see kind of stars doing like orbits that tend to go towards each other and stuff in a way that you could only reasonably explain if there was lensing happening. So that's sort of new. I mean, to date, people have done it with dwarf galaxies. You make some assumptions about how to connect the luminosity of a dwarf galaxy to its infall halo mass, and then you can then measure the subhalo mass function in this way. Stellar streams are a way to do it also, right? If you have the subhalo that hits the tidally stripped wake of a accreted dwarf galaxy, and then it will make a gap in this stream of stars. Yeah, so there are different ways to do it in our galaxy, but unfortunately, the strong lensing in our galaxy is not very efficient because there's not enough distance to make the separation big enough.
Okay, so let's answer that again.
Thanks.